Imagine a vast, dark ocean stretching out before you, its surface shrouded in a thick fog. The water is calm, almost eerily so, and the darkness seems to stretch infinitely in all directions. The fog is so thick that it feels like a wall, limiting your vision to just a few meters ahead. You can only see a certain distance, the point where the fog becomes too dense to penetrate. Beyond this point, everything is hidden, a mystery waiting to be uncovered. This boundary, where visibility ends, is not a physical barrier, but a limit imposed by the fog. This is a simplified way to picture our observable universe. Just like the fog limits our view in the ocean, the vastness of space and the finite speed of light limit how far we can see into the cosmos. Our cosmic horizon is the furthest edge of what we can observe. Our observable universe is not limited by a physical boundary but by the reach of light. There is no edge or wall at the end of the universe, just as there is no edge to the ocean. Instead, the limit is defined by how far light has traveled since the beginning of time. Light has a finite speed. It travels at approximately 299,792 kilometers per second, or about 186,282 miles per second. This speed, while incredibly fast, is not instantaneous. It takes time for it to travel across the vast cosmic distances. For instance, light from the sun takes about 8 minutes to reach Earth. When we look at the sun, we are seeing it as it was 8 minutes ago. This means that the farther we look out into space, the further back in time we are seeing. Telescopes act as time machines, allowing us to peer into the distant past of the universe. The light from distant galaxies has taken billions of years to reach us. When we observe these galaxies, we are seeing them as they were billions of years ago, long before our own solar system even existed. We can only see as far back as the time when the universe became transparent to light. This event, known as recombination, occurred when the universe cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This happened about 380,000 years after the Big Bang. The light from this era, known as the cosmic microwave background radiation, provides us with a snapshot of the universe in its infancy, offering invaluable insights into its origins and evolution. The cosmic microwave background, or CMB, is a faint afterglow of the Big Bang. It is a sea of radiation that permeates all of space. This radiation was released when the universe was very young, hot, and dense. As the universe expanded, the CMB cooled down. Today, we observe the CMB as a faint microwave signal. It is a snapshot of the universe as it was just 380,000 years after the Big Bang. The CMB tells us a lot about the early universe. It provides evidence for the Big Bang theory and helps us understand the universe's composition and evolution. When we observe distant galaxies, we are essentially looking back in time. The light from these galaxies has traveled for billions of years to reach us. By studying these distant galaxies, we can learn about the history of the universe. We can see how galaxies have evolved over time. The most distant galaxies we can observe are seen as they were in their infancy. These early galaxies were smaller and more irregular than galaxies today. Observations of distant galaxies provide valuable insights into the processes of galaxy formation and evolution in the early universe. The edge of the observable universe is not a place we can physically reach. It is a limit set by the age and expansion of the universe. The universe is expanding and the rate of expansion is accelerating. This means that distant galaxies are moving away from us. The farther away a galaxy is, the faster it is receding from us. At a certain distance, the recession velocity exceeds the speed of light. This does not violate the laws of physics, because the expansion of space itself is not limited by the speed of light. It means that objects beyond this distance are forever out of our reach. Section 5. Imagining the Edge, a hypothetical voyage. In this chapter, we embark on a thought experiment, a journey to the very edge of the observable universe. What would we find if we could travel to the farthest reaches of space? If we could somehow travel to the edge of the observable universe, we would not encounter a physical barrier or a signpost marking the end of space. The universe doesn't have a defined edge like a wall or a fence. Instead, it stretches out infinitely, or at least as far as we can observe. Instead, we would likely find ourselves in a region of space that looks very much like the region we observe from Earth. The stars, galaxies, and cosmic structures would appear familiar, as if we had not traveled far at all. This is because the universe is remarkably consistent in its structure. This is because the universe is thought to be homogeneous and isotropic on large scales. Homogeneous means that it is the same in all locations, and isotropic means it looks the same in all directions. These principles are fundamental to our understanding of cosmology. However, the galaxies in this distant region would be much younger and less evolved than galaxies in our local neighborhood. We would be peering back in time, seeing these galaxies as they were billions of years ago, in their formative stages. We would be witnessing the early stages of galaxy formation and evolution. Stars would be forming from cosmic dust clouds, and galaxies would be in the process of assembling and growing. The cosmic microwave background radiation would also appear different. This faint glow, a remnant from the Big Bang, permeates the entire universe and provides a snapshot of the infant universe. It would be blue-shifted, meaning its wavelength would be compressed due to the expansion of the universe. As we move towards the edge, the light from distant objects would shift towards the blue end of the spectrum, indicating that these objects are moving away from us at incredible speeds. This blue shift is a key piece of evidence for the ongoing expansion of the universe. The expansion of the universe is a fascinating phenomenon. It means that space itself is stretching, causing galaxies to move away from each other. This expansion is not uniform, it varies depending on the distance between objects. The farther apart two objects are, the faster they appear to be moving away from each other. This journey to the edge of the observable universe is not just a voyage through space, but also a voyage through time. We are traveling back to the very beginning, to the moment of the Big Bang, when the universe was born in a rapid expansion from a singular point. As we look to the future, the universe will continue to expand, driven by a mysterious force known as dark energy. Galaxies will drift further apart, and the universe will become an even more vast and lonely place. Our hypothetical voyage gives us a glimpse into the past, present, and future of the cosmos, revealing the incredible journey of the universe itself. Section 6. The Expanding Canvas, a Universe in Motion. The universe is a vast, ever-changing expanse filled with countless galaxies, stars, and other celestial bodies, all in constant motion. It's crucial to understand that the universe is not static. It's constantly expanding. This expansion is a fundamental aspect of our cosmos, shaping the very fabric of space and time. This expansion is not like an explosion with a center. It's happening everywhere. Every point in the universe is moving away from every other point, creating a dynamic and ever-growing cosmic tapestry. Imagine baking a loaf of raisin bread. As the dough rises, the raisins move apart from each other. This simple analogy helps us visualize the complex process of cosmic expansion. As the dough rises, the raisins move apart from each other. Similarly, as the universe expands, galaxies drift away from one another, carried along by the stretching fabric of space. Similarly, as the fabric of space-time expands, galaxies are carried along with it. This movement is not due to the galaxies themselves traveling through space, but rather space itself expanding and taking the galaxies along for the ride. This expansion has profound implications for our observations. It affects how we perceive distant objects and the information we gather from them. It stretches the light from distant objects, causing a phenomenon called redshift. Redshift is a key indicator of the universe's expansion, providing crucial evidence for this ongoing process. Redshift is analogous to the Doppler effect for sound waves. Just as the pitch of a sound changes with the movement of its source, the wavelength of light changes with the movement of celestial objects. Just as the pitch of a siren drops as it moves away, the light from receding galaxies is shifted towards longer, redder wavelengths. This shift provides astronomers with valuable information about the speed and direction of galaxies, helping us understand the vast dynamic universe we inhabit. Section 7. The Mystery of the Unknown. The observable universe encompasses all that we can currently detect with our telescopes and instruments. However, it represents only a tiny fraction of the entire universe. There's a vast, unobservable realm beyond our cosmic horizon, a place we can't see because the light from those regions hasn't had enough time to reach us. This unseen universe could be vastly larger and more complex than we can imagine, potentially harboring different physical laws and exotic forms of matter and energy. While we can't directly observe this hidden universe, its existence is inferred through cosmological models and observations of the cosmic microwave background. Section 8. The Ever-Shifting Boundary, a Moving Target. The edge of the observable universe is not static, it's constantly expanding outward as time goes on. This expansion is driven by the relentless stretching of space-time itself. As the universe ages, more and more of the cosmos comes into view. Light from previously unseen galaxies finally reaches us, revealing new regions of the universe. This ongoing expansion means that the edge of the observable universe is a moving target, always receding from us at the speed of light. It's a reminder of the dynamic and ever-evolving nature of our universe, constantly unveiling new wonders and mysteries for us to explore. Section 9. Conclusion: a universe of wonder and limits. The journey to the edge of the observable universe is a journey through time and space, revealing the grand history of our cosmos. We've seen how the cosmic microwave background acts as a baby picture of the universe and how distant galaxies serve as time capsules, offering glimpses of the past. While we can't physically reach the edge of the observable universe, our understanding of physics and cosmology allows us to explore it through observations and theoretical models. The universe, in its vastness and complexity, continues to inspire awe and wonder, reminding us of the profound mysteries that lie beyond our grasp.